Hi everyone, this is Mabarish Dan, and I'm gonna be continuing this part of the chapter. So, the Arene oxide intermediate is an unstable intermediate. It is an active metabolite. It is highly chemically reactive and undergoes many reactions rapidly. Can be seen in the urine. First, the aromatic ring is maintained. Second, hydration reaction to form a diol. It is not aromatic. And third, the glutathione has a high pool availability, phase 2 glutathione conjugation, and the OH in reaction 3 and 4 in the meta position, please keep in mind of this, and the 1, 2, 3 reactions are detoxification pathways, and we have non-toxic metabolites given. The toxic metabolites are given when arene oxide binds sometimes to macromolecules by covalent linkage and creates macromolecular adduct that can covalently bond to the DNA, RNA, or proteins, which leads to potential for toxicity to humans. This is an example for the detoxification reaction for arene oxide. As we can see, the arene oxide undergoes rearrangement, and then finally we have a hydroxyl group at the para position, which is called arenol. For the toxicity of the arene oxides, as we can see in the scheme here, benzo-A-pyrene is metabolized at sites 7 and 8 to give non-toxic epoxide called 7,8-oxide. It's non-toxic. Then, there shall be hydration reactions to give non-toxic metabolites called 7 and 8 trans dihydrodiol. Here we have loss of aromaticity. Then, the 7,8 dihydrodiol non-carcinogenic metabolite will further be metabolized at positions 9-10 to form a carcinogenic 9-10 epoxide that will bind to the DNA and leads to toxicity. More for the toxicity of arene oxides, environmental pollutants such as the PCBs have attracted considerable public concern over their toxicity and health hazards. These compounds appear to be resistant to aromatic oxidation because of the numerous electronegative chlorine atoms in their aromatic rings. This causes inactivation. In addition, polycyclic aromatic hydrocarbons are ubiquitous environmental contaminants that are formed from auto-emission, and they refuse burning and other combustion process. Example, benzo-A-pyrene, which is a potent carcinogenic agent, and we talked about it in the slide earlier. Now for another oxidation reaction, we have the oxidation of olefinic carbons, oxidation of the C double bond C into epoxide, which is subject to enzymatic hydration by epoxide hydrase to form trans 1,2-dihydrodiol in a manner similar to arene oxides, or may conjugate to macromolecules and have toxic effects. Epoxides from olefins, olefinic epoxides, are more stable and less toxic than arene oxides. We have to take note that when we take a urine sample or feces sample and analyze for isolate metabolites, we can see epoxides from olefinic carbons, while arene oxides can't be identified due to being highly chemically reactive and highly unstable. Thus, we can never isolate a chemically unstable arene oxide from urine or feces. An important tip for you is to look at the molecule, and you can see the possible sites for metabolic reactions. For example, if you see C double bond C, which means it's an olefinic carbon, it can be oxidized. Similar to the arene oxides, even though they are not as chemically reactive, epoxides from the olefins may exert some toxicity by attacking proteins and nucleic acids. Example, we can see here, styrene is being conjugated to the styrene oxide, and now we have an epoxide ring, which can be toxic. However, there is a detoxification for the olefinic carbons, which is styrene, which is chemically used in the industry, can be metabolized at the level of the ring or at the level of the C double bond C, which is our concern now, and the major metabolite binds to the glutathione and forms a non-toxic metabolite via phase 2 detoxification glutathione conjugation. This is how the detoxification process occurs, which is the safest pathway to get rid of the epoxide and the arene oxide, which is by the glutathione adduct formation. Now for the oxidation at the benzylic carbons. The benzylic carbon is the carbon which is after the double bond, which is circled here in red. So we're going to be introducing a hydroxyl, which we're going to be having a CH2OH in the case of hydroxysilicoxib. Here the CC is hindered and bulky and doesn't undergo oxidation. In the last molecule below, we have 3 possible benzylic carbons. If you want, you can check them by your own. but I'm gonna do number 1 and the 3-methylcholanthreone. Number 1 is a benzylic carbon because, as you can see here above, we have a double bond, and right after the double bond, which is the carbon number 1, it is a benzylic carbon and can undergo hydroxylation. It is very important to note that the benzylic carbon should be right after the double bond of an aromatic ring. It should always be an aromatic or benzylic ring. So here we have the example for tolbutamide, which has a sulfonylurea derivative and responsible for the antidiabetic action. So for the tolbutamide, we can see here in the CH3 at the para position, it is a benzylic carbon because right before the carbon we have a double bond, so it will undergo hydroxylation and it will form an alcohol metabolite. Same thing for imipramine. Imipramine, we have 2 benzylic carbons and amitriptyline also. Now for the allylic carbon, it is a bit like the benzylic carbon, but the difference is that in the allylic carbon is right after any double bond. However, for the benzylic carbon, it is right after double bond of a benzylic or aromatic ring. For example, here at C7 we have a carbon right after a double bond, and the double bond is not for an aromatic ring, so the carbon can undergo hydroxylation. More examples for the oxidation at the allylic carbons. Let's think about the barbiturate derivative, which is hexabarbital. We have 2 allylic carbons at the position 3' and 6'. However, C3' compared to C6' is more exposed. So we favor the 3' side to form a 3-hydroxy metabolite, which will then be further oxidized and rearranged. But the C6' position is hindered because, as you can see in the hexabarbital molecule, we have another carbon next to it. So if we form the hydroxyl group, it's gonna be hindered. Also, it is important to note a rule for the allylic carbons that the alpha carbon for the double bond should have at least 1 hydrogen in order to undergo hydroxylation. Now for the mechanism of toxicity by the allylic carbons, we have safrole. Safrole has both an allylic and benzylic carbon at the same time. Why? Because, as you can see here, it has a benzylic ring, and at the right side we have a double bond, and the carbon before the double bond can also be allylic. So we have a common carbon for the both benzylic and allylic carbon. So after undergoing hydroxylation, we're going to have a hydroxyl group attached to this carbon. And this hydroxyl group is going to undergo sulfation. We're going to have a no SO3- after phase 2 sulfation, and we get a good leaving group. However, terminal carbon is attacked by a nucleophile of DNA, RNA proteins, and we have rearrangement to form the final toxic product seen above. Now for another oxidative reaction, we have the aliphatic carbons. For the aliphatic carbons, when we see a carbon that is omega, omega means that the carbon is at the end of a chain, which means it can undergo hydroxylation. We can call it a primary carbon. And the carbon right before it, it's omega -1. It can also undergo hydroxylation, but in this case, we're going to be forming a secondary alcohol. And for the omega oxidation, we're going to be forming a primary alcohol. It is also important to note that the initial alcohol metabolites form from these both omega and omega -1 oxidations. They can also form further oxidation to yield aldehyde, ketones, or even carboxylic acids. This is the oxidation further explained, as I said earlier. So the omega carbon is the carbon at the end of the chain. It can undergo hydroxylation, and we're going to have a primary alcohol. Same for the omega -1, which is the carbon right before the primary carbon, and it can also undergo hydroxylation, but here we're going to be forming a secondary alcohol. So we have an example of chlorpropamide. Chlorpropamide has an omega carbon and an omega -1 carbon. So either of them can undergo hydroxylation, and if the omega -1 carbon underwent hydroxylation, we're going to be forming the major metabolite 2'-hydroxy chlorpropamide. Here are more examples for the oxidation at aliphatic carbons. For example, let's take the valproic acid. At the left side, we have the omega and the omega -1 carbons. So if the omega carbon underwent oxidation, hydroxylation, we're gonna have a primary alcohol, which is 5-hydroxyvalproic acid, and it might undergo further oxidation to form a carboxylic group. Now for the omega-1 oxidation, it will also undergo hydroxylation, and we're gonna be having a secondary alcohol, which is 4-hydroxyvalproic acid. More examples for the oxidation at aliphatic carbons, we have this barbiturate, which is pentobarbital. It has an omega carbon and an omega-1 carbon. So the omega carbon can undergo oxidation, and it will form a primary alcohol. However, the omega-1 can also undergo hydroxylation, but it will form a secondary alcohol. Another form of oxidative reactions is the alicyclic carbon oxidation. So here in this ring, we have it is a cyclohexyl ring in a chair conformation. We have the 3 position and the 4th position. So they can both undergo hydroxylation, and in different positions. For example, the hydroxy group can be either axial or equatorial, which is either cis or trans conformation. Alicyclic oxidation is carried out by mixed function oxidases, where the mixed function oxidase tend to hydroxylate at positions 3 or 4 generally. An example of the compounds undergoing alicyclic oxidation are acetohexamide, which is an oral hypoglycemic agent, and glipizide, which is also an oral hypoglycemic agent. So, acetohexamide upper major due to good exposure of the C4 and stereoselectivity of the enzyme. So, this means that the C4 position is going to undergo hydroxylation, which is here shown as the active metabolite. It is trans 4-hydroxy acetohexamide. It can also undergo hydroxylation at the 3 position, whether it's cis or trans, but here the active metabolite is at the 4th position and equatorial. For example, for a piperidine ring, it resembles hydroxylation of a cyclohexyl ring, thus getting oxidized at the C4 position. The example is phencyclidine. It is formerly used as an anesthetic, and minoxidil, which is an antihypertensive agent. The methylene groups attached to an alicyclic ring undergo hydroxylation, generally at the most activated position or at the least hindered position. In cases of cyclohexanone ring, which has an alpha to a carbonyl, a cyclohexene ring, alpha to a double bond, and a phenyl ring, example tetraline, oxidation occurs at the alpha position as discussed under oxidation at carbon atoms, alpha to carbonyls and imines, or amines or allylic systems. Another oxidative reaction is the oxidation of the carbons alpha to carbonyls and imines. So, the microsomal hydroxylation at the carbon atoms alpha to carbonyls and imines is also observed in drug metabolism. The C-alpha is close to a pi system, thus it has good electron density to undergo oxidation. An example of the oxidation of the carbons alpha to carbonyls and imines would be diazepam. Diazepam is an anti-anxiety sedative hypnotic with long duration of action. Its long duration of action corresponds to the metabolism into 2 active metabolites as one reason. This is an example of a drug with 2 active metabolites, which are oxazepam and N-methyloxazepam or 3-hydroxydiazepam. To further understand these metabolites, as we can see first, in the first active metabolite, which is N-methyloxazepam or 3-hydroxydiazepam, what we did is that it undergoes hydroxylation at the alpha carbon, which is next to a carbonyl and imine. The carbonyl group is shown here, and we have now a hydroxylation. However, for the oxazepam, we have the oxidation at the next to the carbonyl, but we have also an N-demethylation, which means that we removed the methyl group which is attached to the N group. Okay, so at this point we have only considered oxidations at carbon-carbon interface. Now we're going to be continuing this part, but we're going to be discussing the oxidation at carbon-heteroatom interfaces like oxygen and nitrogen, in addition to sulfur, which may lead to molecular fragmentation. Okay, so as I said, we're going to be starting to discuss the oxidation involving carbon-heteroatom systems. For example, like CN, CO, and occasionally CS systems. we here have metabolic oxidations for the C-alpha to the nitrogen, oxygen, and sulfur. So the carbon heteroatom oxidation involves two basic types of biotransformation processes. First, we have the hydroxylation of the alpha carbon atom, and we also have the hydroxylation or oxidation of the heteroatoms, nitrogen and sulfur only. For the oxidation involving CN systems, we have the oxidation of tertiary aliphatic and aliphatic amines, which consists of N-dealkylation, which is the oxidative removal of the alkyl group, deamination, and N-oxidation, which is when we hydroxylate the N, we add a hydroxyl group. The CN systems that can undergo oxidation are the aliphatic amines, whether they are primary, secondary, and tertiary, alicyclic amines, aromatic and heterocyclic nitrogen compounds, and the amides. For the oxidation of tertiary aliphatic and alicyclic amines, the tertiary aliphatic and alicyclic amines are metabolized by oxidative and dealkylation. Aliphatic primary and secondary amines are susceptible to oxidative deamination and dealkylation and oxidation reactions. Aromatic amines undergo similar groups of reactions as aliphatic amines, for example, both N-dealkylation and N-oxidation. The functional groups on the alpha carbon determine if we have an aldehyde or a ketone. Carbonylamines are very unstable intermediates that undergo rearrangement into a carbonyl moiety, aldehyde or ketone, and into a secondary amine from tertiary amines. If there R2 was hydrogen, we would get a primary amine by alpha carbon hydroxylation of a secondary amine, and a carbonyl moiety, whether it is an aldehyde or a ketone. Here we are focusing on the aliphatic system and not the aromatic. So we have four options: 3 CN system plus 1 different CN system with one parent molecule, amino derivative antidepressant. Furthermore, we can have N-dealkylation into bis-dismethyl imipramine, and then the RCH2 and H2 can be oxidized by MAO into the COOH and NH3. So here let's take a closer look at lidocaine. It is unlikely to have hydroxylation of the alpha carbon next to the C double bond O to have two C double bond O's next to each other. So for lidocaine, it can undergo two N-dealkylations, active primary and secondary metabolites as antiarrhythmics by alpha carbon hydroxylation, and rearrangement reactions. They look very much like the parent drug, and we can also have amide hydrolysis, which will be later discussed. So for the cyclization of normethadone, we have N-demethylation first within a 3N system open chain molecule, then rearrangement, and the metabolites are all inactive. So for brompheniramine, we're going to have a 2N demethylation reactions, and then we're going to have the bis-dismethyl metabolite, and it's going to undergo oxidative deamination, which is catalyzed by the MAO, monoamine oxidase, to form the 3p-bromphenyl 3-pyridyl propionic acid. Now for the lactam formation. Alicyclic tertiary amines often generate lactam metabolites by alpha carbon hydroxylation reactions. So let's take a closer look at nicotine. In nicotine we can have N-demethylation, and we have one carbon which is more hindered, so we have to favor formation of an amide ring, which is more common rather than cutting, and the intermediate will undergo rearrangement to form the cotinine, which is the lactam metabolite. For phenmetrazine, it can undergo hydroxylation, forming carbonylamine intermediate, and finally we're going to be having the 3-oxophenmetrazine. So some secondary alicyclic amines, like tertiary amines, are metabolized to their corresponding lactam derivatives. So the N-dealkylation of the secondary amines proceeds via carbonylamine pathway, similar to the tertiary amines, and gives rise to primary amine metabolite. Primary amine metabolites are susceptible to oxidative deamination, following the process similar to N-dealkylation. In general, dealkylation of secondary amines is believed to occur before oxidative deamination. In some cases, direct deamination of the secondary amine is also possible. So here we have the primary amine undergoing alpha carbon hydroxylation, forming the carbonylamine. Carbonylamine will undergo rearrangement, and we're going to have the carbonyl and ammonia. For the secondary and primary amines and dealkylation, we have alpha carbon hydroxylation and rearrangement also called N-demethylation, first, then followed by oxidative deamination. We can have para-hydroxylation, also direct oxidative deamination from the start, and a benzylic carbon. For the direct and indirect oxidative deamination, secondary amine here with two pathways for metabolism. We have two alpha carbons, each with at least one hydrogen. We analyze the urine and check for metabolites. Two metabolites and amino group and ketone acetone are all four products. We look for the primary amine metabolite and the NH3. No, we had indirect deamination. If we look for NH2CH, CH3-2, this means that we had a direct deamination. In methamphetamine, we have a methyl group attached to the N group. Then it undergoes N-demethylation to form amphetamine, and then the amine will go, which means N-deamination, and we're gonna have the phenylacetone. It is important to note that if the alpha carbon hydroxylation cannot occur, then the oxidative deamination is not possible, and this is an example for this concept, which is ketamine. Ketamine can undergo N-dealkylation and forming norketamine, but it cannot undergo alpha carbon hydroxylation, so no deamination. Secondary amines may undergo N-hydroxylation followed by further oxidation, yielding the corresponding nitrogen derivatives. It is important to note as a rule that an alpha carbon has to have at least one hydrogen for the nitrogen formation. We can also have direct oxidative deamination of the N-dealkylation at the below two sites on the N or para-hydroxylation or the benzylic carbon oxidation. We have N-hydroxylation followed by double bond formation. So in this case we can see hydroxylamine metabolite. It has two alpha carbon, but we favor the double bond formation with the alpha carbon below, since we would have conjugated system. Conjugation is very much more stable and favored. In primary amines oxidation, alpha carbon has to have at least one hydrogen for this reaction to proceed, and then we're gonna have the loss of ammonia, which is N-deamination. Here in the case of phentylamine, alpha carbon hydroxylation is not possible since the alpha carbon has no hydrogen on it. So no oxidative deamination, also no nitrogen formation, and we have different routes of metabolism. The below metabolites can be transformed into nitroso and then nitro. Okay, so for the nitroso and nitro formation, secondary amine can form nitrone via N-hydroxylation, and primary amine can form N-hydroxylation into nitroso, which is very carcinogenic, and then nitro, if the alpha carbon has no hydrogen. Here the above molecule doesn't have a hydrogen on the alpha carbon, so it cannot do alpha carbon hydroxylation. And we need to do N-oxidation or N-hydroxylation to form nitroso, followed by further oxidation to get a nitro. As a general knowledge, nitrosose compounds are very toxic and carcinogenic. Like sausages, processed food, salami, and mortadella and processed meat, they all have the nitroso compound, and it is very toxic and carcinogenic. For the aromatic amines and heterocyclic nitrogen compounds, we can have para-hydroxylation, N-oxidation, N-hydroxylation, and N-demethylation. Here in the secondary aromatic amines, the alpha carbon has one hydrogen, so it can undergo hydroxylation. We have the hydroxylamine, and then it undergo further oxidation to form the nitrone, and also anhydration to form the hydroxylamine, which is a primary amine. So for the oxidation of primary aromatic amines, we have the example here of aniline, which can undergo oxidation and hydroxylation to form hydroxylamine. But here hydroxylamine is gonna be toxic because it oxidizes iron form of hemoglobin into methemoglobin and can lead to methemoglobinemia. For the mechanism of toxicity of azo compounds, first, an azo compound is N double bond N. This is called an azo system. So first here in the N-methyl-4-aminoazo benzene, the N undergoes hydroxylation, and now we have hydroxylamine. Then this hydroxyl group is going to undergo sulfation, which is a phase 2 reaction, and we're going to have an OSO3-, which is a good leaving group, and the sulfate group is going to leave, forming the aryl nitrinium ion. This system altogether causes toxicity because it's going to bind to DNA, RNA, and protein, and it's going to be very toxic. Examples of toxic azo compounds, we have the artificial coloring for sweets like M&M, and it is not natural and toxic and artificial. For the dealkylation of amides, it is very much like amines. We saw so far diazepam with 3 active metabolites so far. Here we have active dealkylation metabolites, which is nordiazepam, and carbonylamide formed by alpha carbon hydroxylation of diazepam. It is also an intermediate. So what is the importance of alpha carbon hydroxylation and cyclophosphamide? So cyclophosphamide is inactive as such. It is an inactive prodrug that must undergo bioactivation in the liver by the CYPs and undergo 4-alpha carbon hydroxylation into 4-hydroxy cyclophosphamide. It's inactive mainly and has some activity. Then the secondary alcohol undergoes oxidation into its ketone derivative, which is also not active at all. The secondary alcohol exists in equilibrium with aldophosphamide, which is active. Aldophosphamide can be oxidized by aldehyde dehydrogenase into carboxylic acid form. It is inactive. Aldophosphamide can undergo non-enzymatic rearrangement into acrolein, which is toxic, and phosphoramide mustard, which is the most active product of this system, with anti-cancer activity. The second alpha carbon hydroxylation is important in the activity of bioactivation of this drug in the liver. Now for the oxidation involving CO system, dealkylation. The biotransformation involves an initial alpha carbon hydroxylation to form either hemiacetal or hemictal, which undergoes spontaneous carbon-oxygen bond cleavage to yield the dealkylated oxygen species, phenol or alcohol, and a carbon moiety, aldehyde or ketone. So this is an example for the oxidation involving the CO system. First, it undergoes oxidation. And we should make sure that the alpha carbon has 1 hydrogen. Then it undergoes dealkylation. Now we're going to have to be thinking about what are the O demethylation metabolites of phenacetin and codeine. So this is the answer. Codeine is going to undergo an O demethylation, and we're going to have morphine, and both of them are active. And for phenacetin, it will also undergo O dealkylation to form acetaminophen, and both of them are active. Now for the oxidation involving carbon-sulfur system, the carbon-sulfur bond will have to break, and we're going to have an S dealkylation, alpha carbon hydroxylation followed by rearrangement, and the products are thiol and carbonyl. For the carbon-sulfur system, we have very common reactions like the conversion of the C double bond S to C double bond O, and the thiol system into the oxo system in case of thiopental to pentobarbital. Here are a few examples of these reactions. For example, thiopental, we have the C double bond S and the formation of pentobarbital by the conversion of C double bond S into C double bond O. So in the case of thioridazine, first we have an S oxide, S double bond O. We have a sulfoxide, ring sulfoxide, and the S double bond O is converted into a ring sulfone. We have now S double bond O, double bond O. Also, it can become a sulfoxide, which is the S-methyl double bond O, and the conversion to sulforidazine, which is a sulfur dioxide, sulfone. We also have other oxidative reactions like oxidative dehalogenation. It requires 2 halogens on a carbon. If we have 3, there is no hydrogen available to replace. With 1, the reaction generally won't proceed, and the intermediate acyl halide is very reactive. Okay, so it is very important to note that we shouldn't inhale chemical fumes in the lab, and we should wear protective cover mask to cover the nose and mouth. So in this reaction, the best leaving groups are Br. Br being the superior, then chloride, and then CF3, which is the least best leaving group. So, look at this as if C-Heteroatom system. Look for one better leaving group. Halothane is toxic. It causes liver toxicity due to metabolism into toxic chemically reactive species. An intermediate called trifluorochloride, which is very toxic and easily attacked by the DNA, proteins, and RNA. Because the carbonyl carbon is very electrophilic, especially due to the electron withdrawing group CF3 and chloride. Chloroform example, it is very toxic and causes liver and kidney toxicity and brain tumors. the carbonyl carbon and phosgene is attached to two electron withdrawing groups chloride. Molecule is very chemically reactive and is easily attacked by nucleophile of the liver, kidney, and proteins. And finally, for the oxidation reactions, we have alcohols and aldehydes. For example, primary alcohols, the carbon is well exposed here. Oxidation of primary alcohol generates aldehydes, and the oxidation of aldehydes generates carboxylic acid derivatives. For the secondary alcohols, carbon is not well exposed. Oxidation of secondary alcohol to ketones is not often important as it reduces back to secondary alcohol, and the secondary alcohol group being more polar and functionalized is more likely to be conjugated than the ketone moiety. So now we're done with the oxidation reactions, and we're going to start to discuss what are the reduction reactions. So just as a reminder, we're now talking about the phase 1 reactions. We discussed the oxidation reactions, which consist of aromatic moieties, benzylic and allylic carbons, and the C-Heteroatom System, in addition to other reactions. Now we're going to be focusing on the reduction reactions like aldehydes and ketones, nitro and azo, and miscellaneous reactions. This is an example to point out that reductive reactions are less common and oxidation reactions are more common, and more polar metabolites are formed. For the first reduction reaction, we're going to be talking about the reduction of sulfoxide to sulfide. Sulfoxide can be reduced into sulfide, and sulfoxide can be oxidized into sulfone. Second, we have the reduction of nitro and azo compounds. So here we have the nitro, which is reduced to nitroso, and then we have further reduction to hydroxylamine and forming a primary amine. Please note that this is a reversible reaction. But the more common and direct reduction is the azo, which is reduced to hydrazo, and finally we have the amine, primary amine. Here in protonsyl, we have N double bond N, which is the azo compound. It can undergo reduction to form the sulfonylamide and the 1,2,3 triaminobenzene. Please note that protonsyl is an antibiotic and a prodrug which is inactive, and it has a hydrazine moiety, so it is a hydrazine derivative. Now we know more about the oxidation reactions and the reduction reactions. And finally, we're going to be discussing what are the hydrolysis reactions. As we said earlier, we discussed what are the oxidation reactions, same thing for reduction reactions, and now we're going to be talking about the last part of phase 1 reactions, which is hydrolytic reactions. So the concept of the hydrolysis reactions is that we're adding water to esters and amides and their isosteres, and the hydroxyl group from water ends up on the carboxylic acid or its isostere, and the H in the hydroxy or amine. So we have several reactions in the hydrolysis reactions. We have ester hydrolysis, we have amide hydrolysis, which is slower, and carbonate hydrolysis, carbamate hydrolysis, urea hydrolysis, and hydrazide hydrolysis. Here are a few examples of drug hydrolysis. For example, we have aspirin. Aspirin hydrolysis is very rapid and common into salicylic acid and acetic acid. And hydrolysis is a very common reaction. The duration of action is dependent on the metabolism, to tell which is short or long-acting, which in turn depends on stability. So it's very important to note that here, for example in procainamide, it is longer acting than the procaine, because procaine has an ester group, however procainamide has an amide group, and the amide group is longer acting than the ester group. Stereoselectivity of hydrolysis, for example etomidate, the dextroisomer is more rapidly hydrolyzed, but the levoisomer is more rapidly hydroxylated. Okay, so here we have 2-acetyl aminofluorine. It is a very well-known hepatocarcinogenic. It undergoes an hydroxylation reaction catalyzed by CYP to form the corresponding N-hydroxy metabolite, also called hydroxamic acid. Hydroxamic acid undergoes conjugation to form O-sulfate ester, which ionizes to generate the electrophilic nitrinium species, which is toxic and will be attached to the DNA, and it is very toxic and causes damage of the DNA. Finally, and to summarize, When the drug enters the body, it will undergo absorption, distribution, metabolism, and excretion. And today we discussed the metabolism, and we talked about phase 1 and phase 2 reactions. Okay, so thank you guys for watching. Stay posted for part 3, and if you have any question, please ask me in the comments section.